Hello everyone. My name is Aaron Pasterski and I'm here with Jonathan Hernandez to talk to you about HVDC technology. We both thought the topic sounded pretty cool in class and decided to explore it further. This video covers a brief history of DC and how it relates to AC. Why did a high voltage motivate us to develop an AC grid, and where does that leave HVDC today? We'll then discuss the advantages and disadvantages of DC and offer some sample calculations. Why don't we switch if DC losses are lower? Lastly, we want to show you a few of the big HVDC projects happening around the world today.
1882, Edison used steam-driven DC generators to supply power in a 1 square mile area. The development of a 3-wire 220-volt DC system allowed for a marginal increase in transmission distance and loads, but with these increases came voltage problems. These limitations were overcome in 1885 by William Stanley's commercially practical transformer, allowing for high voltage and low current transmission, and Tesla's paper on two-phase AC induction and synchronous motors in 1888 led to the adoption of the AC system we use today. However, thanks to power electronics, high-voltage DC transmission allows to overcome some of these limitations that AC now faces, such as the high transmitting.
Okay, so now let's cover some of the advantages of DC. The first is that losses are minimized over a distance. Wires have a built-in resistance that will steal power from both AC and DC transmission. However, the lines also have a built-in inductance and capacitance, and this affects AC much more than DC. Due to the charging and discharging of the line capacitances, AC distribution accumulates additional losses from corona discharge and excess current drawn. Linking systems is also much easier with DC transmission. In order to connect two AC electrical systems together, the two systems must be matched in frequency and phase. DC doesn't have this issue, and thus DC transmission removes the necessity of the two synchronized systems, with each one attaching to the DC lines independently. Finally, submarine terrain cables are those that are underground or underwater. These cables have a much larger built-in capacitance and inductance, which leads to even higher losses for AC. The break-even distance between DC and AC is much shorter in these cases, and the picture you can see the size of some of these cables.
However, the bulk of cost comes from the expensive and complicated DC converter stations. For a 2,000 megawatt transmission, a converter station is estimated to be $250 million.
This slide really shows how most HVDC systems are implemented to be attached to an AC grid. In this case, AC power would come in and be converted up using transformers to a very high voltage. From there, we use a series of rectifiers to convert that AC signal into a DC one, and that is the energy that is actually transmitted through the HVDC line. At the end of the transport, we'll convert it back down to AC, and then use that to transmit AC power to the grid. So the HVDC technology is only in this transmission part, and we'll show next with a calculation that the transmission is cheaper in parts, but in order to justify building these two converter stations at either end, we have to save a lot of money in losses via those transmission lines.
Let us compare the power delivered in the transmission lines between a 2-wire DC system and a traditional 3-wire AC system. We shall assume that the transmission lines are of equal length and conductance. The lines are thermally limited so that the DC current is equal to the RMS AC current, and the DC voltage is equal to the peak AC voltage. Also, the system is operating at a power factor of 0.945. Taking the ratio of the DC power over the AC power, we can cancel out the voltages and currents, leaving root 2 over the power factor. This equals 1.5. So 1.5 of the power in an AC conductor can be delivered in one DC conductor. DC only needs 2 conductors rather than AC's 3 to deliver the same power, thus requiring only 2/3 as many insulators. This also reduces the size of towers, bringing the cost of DC 33% less than AC in transmission for the same capacity.
China is considered to be the largest investor in HVDC, with a number of major projects proposed between 2012 and 2020. The Zhangjiaba Shanghai line is the largest to date, and you can see it in the picture across central China. ABB and Siemens are the world's leading HVDC companies, and they contract all over the world. ABB is also working on a technology that they call HVDC Lite. This is basically a smaller scale HVDC technology and is meant to compete with AC over shorter distances. It will be interesting to see how this grows in the future as well. Lastly, I'll take you guys back to an image from a previous slide. This map represents the proposed HVDC system in Germany. Following Fukushima, Germany committed to a plan to decommission all of their nuclear power plants, which would leave some of their major cities without power. HVDC lines are being used to distribute the power over long distances instead of building new power plants.
It would be too expensive and impractical to switch straight from HVAC to HVDC, since it would be a logistical nightmare and some devices rely on AC power, such as appliances. However, the techniques could be used in tandem, such as relying on DC for transmission and AC for distribution. DC's relation with renewables can be crucial, especially if generation is done in far-off isolated areas. With solar farms, no conversion would be necessary for transmission, since solar outputs DC power. And with offshore wind farms, submarine DC cables can be used because of their higher capacitance than AC cables.